It's Not That Simple is back with another fascinating interview. Today we're talking science and we're talking technology. Can you program organisms and cells much like you do computers? Can technology help us create our own viruses and medicine at home one day perhaps? And if so, how does synthetic biology help us do all of that? These are just some of the many questions that we're going to ask today's star guest as we focus on biotechnology and try to break it down, explain why it is not that simple. And we know it's not that simple, of course. We're delighted to have Andrew Hessel with us. Andrew, you're a distinguished figure, of course, in the realm of genomics and synthetic biology. You've been making really big strides when it comes to advancing human and animal health through cutting-edge innovations. You're president of Humane Genomics, also a serial entrepreneur. Let's get right into it because this is such an interesting topic and one which I'm really looking forward to learning much about. Let's start with some basics on how you got into this path, because you studied biology, but then you became an entrepreneur and focused on biotechnology. So how did that happen specifically?
That's a great question. I actually never planned to be a biologist. I loved everything mechanical, electrical, computational. I fell down a hole with the personal computer when it was first released. And as I was playing with all these other technologies and going through my schooling, I had to start to focus, and I realized that all the stuff that I was working with was stuff that humans made, and so someone understood them really well. But biology was mysterious. No one fully understood it, and yet I could see parallels to what I was doing in computers, particularly in the world of biology. So I thought, that's it. I'm going to focus on biology, but I'll do it bottom up and work with the simplest cells, the microbes, and study the cell biology and their software, which we call the genome.
So technology obviously has played such a crucial role in all of our lives in recent years across so many areas, and obviously it's now so influential in the biology landscape as well. One of your main interests is synthetic biology. Let's start with a quick definition for us.
Yeah, synthetic biology isn't synthetic at all. It's still natural biology, but we're building it where it's constructive. So we borrow the term from synthesis and being able to build. I particularly like it because most people have heard of DNA sequencing, but they haven't heard of DNA synthesis, actually putting together the molecule. And the core technology for synthetic biology is the ability to write or edit DNA code.
So this is crazy. Okay, I'll be honest with you. This is crazy for me because when you talk about editing genome technology, we've known about that for more time, but now you can also pre-program them from scratch.
Yeah, so you have to think of, well, I find it helpful to think of the cell as kind of a computer. It's not like the computers we use every day, but it's a processor. A living cell, and again, I tend to start just with simple cells like microbes. They sense their environment, so those are inputs. They react to it. Those are outputs. So it's kind of a computer. It's kind of a molecular processor. So it's very busy. It's always doing something, building something, breaking something down. And there's a program that runs the cell. It's always written in DNA, which is a molecule itself, but it's a physical string of digital code. Not zeros and ones like we have with computers, but with chemical bits that we abbreviate as ATGC. But it's the same as think of it as a very long sentence, or but it's truly a code, a software that runs all the metabolic processes of that cell. So if you can manipulate that code, either to edit it or with DNA synthesizers, write it from scratch, you have the ability to program the cell and what it's doing.
Okay, so there's so many things I would like to unpack from that. But first of all, When you talk about artificial genomes, do you think, or what do you think will be able to be synthesized or created?
Anything that biology can make. Anything that biology can make. So any protein, metabolic pathway, or organism is within reach if you can start to write genetic code. And you have to think of it like a book. If you can only write a sentence, then you can only you can only do something simple. And in general, the smallest functional component of biology is a protein, a single protein, and those are generally about 2,000 bases of genetic code. So we've been writing proteins for decades. And in fact, today, as our technology for doing synthetic biology has improved, we're probably in this golden age of protein engineering. My particular interest, though, is being able to write a complete genome or a complete program for a particular organism. And in general, that's a much larger code base, think of it that way. And probably the smallest free-living bacterium is about 500,000 bases of genetic code.
Okay.
And more on the average size of a microbe, it's more like 5 million bases of genetic code. We've demonstrated that we can do that we can build cellular genomes, but it's just not fast or cheap to do that yet. So we're still very early in the world of synthetic biology, or what I'm increasingly calling today digital biology, because this manipulation is largely done with software tools and robots. But we're still in the early days, but we're absolutely able to program biological molecules, and the number of the size and complexity of these of what's within reach is growing as our technology increases.
Now, you're very much involved in the Genome Project, right?
Yes.
Project. What is the goal, and what do you hope to achieve, and also what's the time frame, what kind of timeline you have?
Yeah, the Genome Project, right, was founded really to be the other side of the coin to the Human Genome Project, which the Human Genome Project, which started in 1990 and was formally completed in 2003, was a huge effort to go and read the human genome, ultimately giving us insights to our biology in sickness and in health, but really catalyzing the development of tools and technologies and processes that allow us to read all genomes, all DNA. But I recognized, along with a number of colleagues, that we didn't have the same level of investment in the other side of the coin, which is synthesizing DNA, being able to string together genetic programs to make proteins or fix diseases or build organisms. So there were groups doing this, but they weren't getting a lot of attention. The first viral genome, for example, was written in 2002. The first bacterial cell genome had been written in 2010. And in 2015, I attended a meeting where scientists from around the world were synthesizing the genome of yeast, just baker's yeast, like we use for making bread or beer. And no one was paying attention. So I proposed, well, why don't we say we're going to synthesize the human genome? We can start. We have the tools to start, not to finish. It attracted a lot of attention and investment from around the world to start moving in that direction. So basically, because we're humans and we tend to be human-centric, saying that you're going to write a human genome really motivated a lot of people and got people interested. But I want to be absolutely clear: we're nowhere close to having the technology to do that yet, and we weren't aiming to make designer babies. Many human cells can grow in a dish. It was all about learning how to chromosomes that are kind of human scale length.
Okay, so right now we're able to create from scratch cells, microbes, viruses. How accessible is this technology, and what opportunities and threats are there in this realm? Because when you talk and you mentioned there work that can be done with diseases, in an ideal world, and I don't want to put a time frame on it, but how could these cells or how could these viruses or bacteria help humans live healthier lives?
Absolutely. Well, first of all, this is a living world. Like, biology runs this planet. It's the oldest technology. It's been around for billions of years. But it's also the most mysterious technology because it's the only technology that we didn't build. It built us. So it's always a little mysterious to us, and it's the only technology that really comes with a lot of baggage. No one claims you're playing God if you're making a new phone. So biology is a provocative technology. But scientists from around the world, biologists, have been reverse engineering it, taking it apart and trying to understand it for hundreds of years. And what's changed is now our tools and our systems have gotten so good that we can analyze it at a molecular level. And yes, today we can build proteins from scratch. Those are just, think of it as components in a car or a phone. We've demonstrated that we can build a virus. I call viruses the most sophisticated pen drives, USB drives. It's how you load code into a living cell. Now, most people immediately think that code is malicious, but I want to be clear, if it wasn't for viruses moving chunks of code around the living world and the cellular world, you wouldn't get rapid evolution.
Right.
They're real agents of evolution. And we've demonstrated that if we string together a large enough program, we can actually create a program for a microbial cell. That's the level that we're at today. Everything else, if we're engineering a plant cell, if we're engineering a human cell or an animal cell, there we're not synthesizing the whole genome, we're just making an edit. And many people have heard today of CRISPR, which won the Nobel Prize a few years ago. CRISPR gene editing is our ability to basically cut and paste chunks of genetic code, allowing us to make changes, correct a disease, enhance a cell to make a particular protein, for example. But it's really just small changes that we're making to a much more sophisticated genome. But with this technology, editing and writing, the entire living world opens up. So we can start to reprogram a cell, a simple cell like an E. coli, to make a medicine. We can correct a genetic disease, a gene therapy. We can make a plant resistant to a particular fungus or other pest. The more we do, the more we become adept at this type of engineering.
Growing up, when you watch science fiction movies and you kind of imagine these apparatus that you can use that automatically tell you what's wrong with you and can start fixing that artificially, are we, something that seemed really that would only be present in these science fiction films, are we getting closer to a scenario where, whether it's through apps on our phone or whether it's through some kind of scanning machines with synthetic biology and biotechnology, that we can start not only monitoring our health, but constantly improving it or maintaining it?
Oh, I think so, absolutely. Like, just look at DNA sequencing, for example. And again, we only sequenced the first human genome, at the turn of the century.
Right.
So the technology's only been around for a quarter century. Today, DNA sequencing is used routinely from everything from tracking viruses like COVID as it spread around the world and was mutating and we were getting all the different variants, to understanding what's causing a child to be sick when they can't explain it themselves, they're a baby or a toddler, to diagnosing what exactly has gone wrong to cause a particular cancer. Reading DNA is really our best microscope into the living world. It's giving us, it's like opening up a software program and saying, what's wrong with this computer? What's corrupted in this software? So that's, but even now, DNA sequencing, which has been one of the fastest advancing technologies ever, you know, going from $3 billion to read the first human genome to today, you could get your genome fully sequenced really well under $1,000.
Really?
And I think the record for sequencing and analyzing a human right now is 5 hours.
And what does that look like?
You know, it just looks like code. It's computers that analyze this work, but you know, isolating DNA is a 10-minute procedure. Loading it into the machines that read and digitize the DNA it's all done automatically now, and the analysis is done automatically. So just reading DNA is changing medicine and our ability to monitor the living world around us. But when you can turn around and start to write code, now it becomes creative. Now you have the ability to affect it. So instead of just diagnosing a disease, now you have the opportunity to cure it, which is huge. Instead of just understanding, you know, the microbes in our mouth or our gut, now we have the opportunity to engineer those microbes to, you know, keep us healthy. You mentioned, well, how accessible is this technology today? It's nowhere close to being able to program a computer. The ability to program computers was once a very elite field. In a recent presentation, I noted that some of the first computers to really make it big, and on the cover of magazines, and I remember this, was a computer called the Cray 1. They cost about $8 million at the time. This is where I'm talking 1975 era. And they were hand-built, beautiful computers. And people, they sold about 100 of those systems, and they're amazing. But that didn't change the world of, you know, only very few people could afford a computer. But just a few years later, we started to get the microprocessor available, essentially a computer on a single chip. And that led to the PC
Personal
revolution,
computer.
Apple and IBM and other
and that
groups.
changed our lives.
And that brought in millions of developers. So today we're sitting at that transition. Synthetic biology or digital biology is not accessible. No one has DNA sequencers at their homes, and very few people sit down and program DNA. If I had to round them all up in the world, it would be a few 100,000 people. But the technology has been advancing extremely quickly, and it's becoming more accessible. So this is not going to be the most high-powered genetic engineering, but I believe that we're about to get to the point where we can start to build the introductory digital biology or synthetic biology to start training a new generation of biological engineer.
When you were talking about ways in which this technology can help us cure certain diseases or address certain weaknesses in our systems, I started thinking about the song Forever Young, right? Because we also know that aging is a genetically controlled process. Is it possible to synthesize a genome of a human that simply does not age?
That's a great question. There's a huge interest right now in aging and can it be manipulated? And the evidence is yes, it can when we start working with everything from simple organisms like roundworms all the way up to mice. Even dogs now. The first clinical trial to essentially reverse aging in dogs is underway now. To be clear, the Food and Drug Administration, which regulates pharmaceuticals, doesn't consider aging a disease. They consider it a natural process. So this clinical trial in dogs is a breakthrough.
Wow.
Just to get people to start thinking, like, can we manipulate this? I believe we're going to have make huge advances in the biology of aging and understanding aging to better regulate it, perhaps drug aspects of it to keep us healthier longer. But I don't think we're going to dramatically change the arc of our aging, because that's, as you said, it's built into our genome, and we're born with that genome. So until we can start to engineer our genome, I don't think we're going to change it dramatically. But that being said, even now, even if we had the ability to write a complete genome from scratch and make an embryo and grow a baby, we wouldn't know how to program that baby to live longer.
And all the stages as well.
Yeah, so we have so much biology to learn, but right now, because we're learning quickly and because all biology runs the same code and all cells in all animals, all creatures have the same basic features, everything we learn in life science, in working on any organism, really will pay benefits to human biology.
Okay, so we focused most of the conversation so far on the opportunities and I guess the positive implications of these changes that can occur in our bodies, in our systems, in our cells. But obviously when you talk about viruses, it hasn't been that long since we had one of them, and you made reference to that, stop the planet, pretty much. So when you start getting into this technology, and I don't want to call them evil agents, but interests that can be present to use this technology for negative purposes or evil purposes, how aware should we be of this threat?
I think we need to be much more aware than we are. I read a really wonderful overview recently by the head of the RAND Corporation, a fellow by the name of Jason Matheny. And along with Roger Brent and another colleague, he wrote a paper in Foreign Affairs that summarized it really well. But we can think of COVID almost as put this way, you can draw a lot of parallels between programming biology and programming computer systems. When we first started to make computer systems and network them together, we realized very quickly that we need security. And we needed antivirus software, and today that antivirus software is extremely
Firewalls
intelligent. It's all AI powered.
Okay.
Now, biology also has defenses. You can think of it as biosecurity systems. Even CRISPR gene editing is actually part of a microbial defense against viruses. So we have our immune systems. We constantly scan for biological threats, and most of the time it works properly. But some viruses and some bacteria do manage to get past our defenses. If it's a bacterium, we have lots of antibiotics. Penicillin was a game changer, and today we have many, many antibiotics. And even though there are, sometimes we run out of them, or sometimes we encounter a bacterium that is resistant to most of them, we can always make more. When it comes to viruses, we have very few defenses because viruses aren't alive. You can think of it as, again, as a USB stick that loads a program into our own cells. And if that's a malicious program, it's going to take it over very quickly, and it's going to produce a lot more viruses, and we get a viral infection can spread very quickly. Viruses have extremely tiny genomes, and we've been able to synthesize, we synthesized the first virus over 22 years ago, and we didn't immediately start a huge antivirus effort. So today, COVID caught us off guard in some ways because we hadn't had a pandemic in a century, and even though we had prepared, we do many preparations for epidemic disease. Ultimately we realized they weren't that effective, and so that was like a penetration test in cybersecurity, where a bank might hire a hacker to see if they can get past the defenses. And in this case, COVID got past all of our defenses very quickly and shut the world down. We were lucky, even though millions of people died, even though it cost trillions and trillions of dollars in damage and disrupted our lives, it wasn't that bad a virus. Mortality was under 1%. And ultimately
It was
the
just
demographics.
how contagious it was, right?
Yeah,
it was something that we had never seen before.
It was something we had no immunity to.
Right.
It was a brand new virus, so we had no natural immunity. We
What
had
were
no
you
vaccines
thinking
for it.
then? What were you thinking at that time,
I
Andrew, when you were working in this, obviously in this landscape, you've got so much access to information and technology. What were you thinking about the way that we dealt with it?
So it was interesting because I saw COVID emerge, as most people did, but I saw it a little early because I have a company I founded that designs and builds viruses as anti-cancer agents. So I was paying attention to the viral world. And in January of 2020, when that virus was first reported as spreading in Wuhan, China, and then moving into Europe, I was tracking that very closely where a lot of people just wasn't aware of what was going on. And immediately I recognized this is not a normal outbreak. The way the Chinese were responding to it, the way it was spreading, how fast it was spreading was not normal. And so I realized this was going to be a problem. And then I ended up going to a meeting at the end of February in Washington, D.C., at the National Academies. And it was for the Defense Department. And I was surprised because the Defense Department was still unaware at that time that we had this invader.
Wow.
That was attacking the United States. It just hadn't been identified yet in the United States. But if it was spreading through Europe, if it was spreading through China, because we're so interconnected now with our air travel and spreading people around, of course it was there. So I said to the Defense Department, you can detect a missile launch anywhere on the planet and you have countermeasures. You don't have anything. No. You can't detect this virus, and you've got nothing other than hand washing and isolation as really a defense. And so, so fast forward to today, people are much more aware of that we need these things. We need better real-time tracking of the particles around us. And we need to be able to make vaccines faster, and we need a bigger arsenal of defenses. But we haven't invested at the same level that we did for, say, atomic weapons, for these atomic scale weapons.
Should we be concerned? I mean, let's fast forward a few years as the technology you're working on continues to progress and evolve. Surely it can also have an important role to play if there is another outbreak of whatever virus that may be, because some of the historians that we've talked to here on the show, some of the political experts, some of the economists, everybody said that one of the biggest threats of our planet now, moving forward, because of climate change as well, because of how quickly our planet is changing its health and its overall condition, that viruses are a big threat to the planet. So how can the technology that you work on help in combating this, not only raising awareness to it because of the work you're doing, but can actually help fight it and contain it if it does happen again?
I think it's really going to take sitting down with a group of pretty much every leader and the technologists involved, and say, let's just start with a blank sheet of paper and think, how do we deal with this? Because if we can't deal with these small particles, again, with the smallest amount of code, the digital biology, the synthetic biology industry is not going to be able to thrive. Every step change in the technology makes it faster, cheaper, easier to use, and now with AI systems, easier to design. So we really need to think, how can we detect the particles that are circulating around us? How can we think of it as smoke detectors? You know, we have smoke detectors, and that keeps our buildings from burning down because we get early warning when there's a fire. How do we have early detection that there's new particles, something has changed? When people show up sick at the hospital, how do we immediately identify what it is? When my kids get sick, you take them to the doctor, they just kind of shrug. If it's not flu,
Right.
which they have a
You're
rapid
so
test
right.
for, or COVID, which
Yeah.
they have a rapid test for, they just go home. And there's no real antivirals that they can administer. So we need more utilization of our genetic tools to be able to do a rapid diagnosis, and you can do this sometimes in a very passive way. Sewage testing is turning out to be one of the best ways to do population scale testing of the viruses that are circulating.
Okay.
And they do this now. Some companies do this now just with the when they service airplanes. And they empty the tanks on airplanes, they run it through viral sensors. And that gives you a sense of not only what viruses people on the planes may be having, but going right back to their home countries, because you can track that around. So that's a big part of it. But at the end of the day, we're going to have to, we can't wait 9 months or a year for a new vaccine.
No.
We're going, thankfully, the mRNA vaccines were a huge game changer in our ability to make vaccines quickly, because really with mRNA vaccines, you're just writing a short fragment of molecular genetic code, in this case RNA, not DNA, and we're using our own cells as the manufacturing plant. So if we can miniaturize that technology for making mRNA and connect it digitally to our health services, we might be able to get viral updates as easily as we update the software on our phones.
Wow.
And that's one way to contain an outbreak, because usually they always spread geographically. It's another way to give people personalized vaccines and other treatments as well. So that technology, the mRNA technology, could be huge in how we move forward and move past what I just think of as the virus problem. But it's really going to take a reimagining of global public health and a level of cooperation with countries and health units that I think is going to be a real challenge, given some of the divisive politics and policies of different countries today.
Andrew, I wanted to get back into the engineering of the human genome and synthetic biology around that. Obviously, there's the scientific element of it, but then there's the ethical element of it too. When it comes to the advancements that you make and the testing of different processes that you go through, how much do you have to argue for that, and how much is it accepted? Just the simple work that you can be doing in a laboratory when you talk about editing and creating human DNA?
When it comes to the ethics of bioengineering, you rarely run into a problem unless you're working with human biology. If you're working with microbes and plants, for example, there's almost no ethical review. It's not, and yet some of the development of those tools and technologies and even the things that you're working on could potentially have harm. Most people, most researchers, most developers are working to do something good. There's a lot less malicious intent out there in life science than in other areas of technology at this present time. But I think we have to be realistic that if the internet taught me anything, it's that anything that can be done will be done, and people like to hack systems. So as these tools become more democratized, I think we're going to find people self-experimenting more, which as an adult, there's very little you can do to stop that. I think in some ways that can be a very positive force. And then there will be some that come along and will abuse the technology, either for political, religious, or financial gains or motivations. So I think we just have to be realistic there. But when it comes to when it comes to the ethics of manipulating organisms, I think it's tricky because ethics the ethical spectrums are not consolidated. It's a very wide spectrum sometimes. So ethics, what I like about it personally is that it really reveals the spectrum of thought around a particular action. And I think that's that type of engagement is crucial when you start talking about the future of humanity.
Do you think the public is sufficiently informed, though, about the implications and processes of synthetic biology and bioengineering? I mean, obviously, this is still how shall I put it? It's still a science that is not, the process is not complete. You don't know where it's going. So, how do people react to it, and are they sufficiently informed?
I don't think they're sufficiently informed today. In fact, biology is still the most mysterious technology. That being said, so I think this is a generational shift, multi-generational shift.
Because of the technology itself as well, right?
Yeah, you know, even the simplest cells that I study, the microbes, are more advanced than any human technology. They literally self-assemble. So we're talking, if our phones could self-assemble and replicate like a bacterial cell, we wouldn't have to manufacture them. We'd only have to make the first one and let it go free. You know, this is truly an advanced technology, and it's been a huge effort to reverse engineer it to get to this point of understanding. But it's still a very elite area of R&D. I think that changes over the next 10, 20, 30 years as we get a new generation coming in that understands that, you know, just starts from the ground zero that we can program proteins, metabolic pathways, or organisms. Right away, that's a foundational shift in our thinking of biology. We used to take it apart, now we can build it. So I think the people coming into the field today have huge opportunities, and they will do amazing things with it, and there will, of course, be abuses and accidents, hopefully small and contained, that it'll just generate so many different stories that today, I expect that in the decades ahead, programming biology, digital biology will be as familiar to us as computers are today, as the phones in our pockets are today. There is no endpoint. Our phones are still evolving, our technology is still evolving, and what we're doing with biology today, it's just the beginning, but it's going to change the world.
Last question. I want to know how artificial intelligence is changing your industry, and also the speed at which you can work and which scientists are evolving their processes.
So the cell is the most complex machine in existence. It is truly beyond human understanding to fully have a holistic view of the operation of a single cell today. But it's not out of reach for our AI tools. And so our computing systems are now giving us an incredible understanding of the biological systems. They also read every paper, every book. Yeah. And so just assimilating all that knowledge, it's native for these computers. And so we've trained, groups have already trained AI systems on the entire corpus of biology. This led to one of the first real breakthroughs of AI in biology, which was predicting the structure of proteins. It was Google's DeepMind group that really made the first breakthrough in that, I believe, around 2018, where they won a protein folding competition that's been held by scientists for decades. And then literally within 2 years, they solved the structure of every protein. So like the protein world now has computationally been solved. It's already advanced to the point where these AI tools can now design proteins and novel proteins.
On their own?
On their own. So if you want a protein of a particular function, it can now design it. It can run evolution in the computer and make a new protein. So that's huge. This is why I'm saying we're in this golden age of protein engineering. And our synthetic tools are sufficient that we can take a design for a protein and we can quickly turn it into a protein and test it.
Okay.
So we can go from bits to atoms, so to speak. We can go from virtual to reality,
Wow.
which is huge. And as these AI systems continue to evolve, we are going to move to the cellular scale. And already we're using AI in drug discovery, in repurposing existing drugs for new applications, for diagnosing diseases. There's been a number of cases of people just using the chatbots today to telling them their symptoms and being able to get a diagnosis that has eluded their doctors. But the thing that I really like to point out is our AI tools will understand biology better than any human and will have an increasing role in monitoring the world, in monitoring our own health, and in designing pretty much everything we do biologically going forward.
All right. Andrew, we have 4 quick-fire questions for you that we ask all our guests. So in one word or in one sentence, I'd like you to answer the following. The first is, what is one quality that a good leader could really benefit from having?
A good leader can really benefit from being curious.
What is the biggest challenge that the world is facing today?
The biggest challenge the world is facing today is that people are having trouble being optimistic about the future. In my own life, I have seen things continually improve, and yet many people think we're going to go off a cliff. I think we are at the start of something incredible.
If you could change one thing in the world by magic, what would that be?
The price performance of DNA synthesis technologies.
Yeah, that would accelerate, I guess, your
It would
work.
accelerate across the board the things that I love.
Incredibly, yeah. And finally, what's the biggest learning of your life and or career?
I have to say, it's been making human beings. I have 2 children now, and until I had them, I don't think I really was a biologist.
And now you can actually watch their cells develop and evolve in person, right?
They were made in a lab. They're both IVF babies.
Oh, okay.
So I've seen them just as a little ball of cells, and now I get to play with them every day. Yeah.
Incredible.
Yeah. No, it's remarkable. I'm old enough to remember when there was the very first test tube baby in 1978, Louise Brown, born in the UK. And today we don't even know how many IVF kids there are because we don't keep accurate track, but the last estimate I saw was about 13 million.
Wow.
Yeah, so it's huge changes ahead for humanity.
Andrew, it's been truly fascinating to have an opportunity to kind of delve into your mind and also your experience and expertise to share so much knowledge regarding a topic that so many of us don't know certainly enough about, and trying also to make it a lot simpler than what it can seem to be. So it was a real pleasure.
Thank you.
We're going to wrap up another riveting conversation here on It's Not That Simple. Biotechnology was today's focus, and hopefully now you'll be more informed than you were when we started the show. See you again soon. Take care.